Hi, it's Jason Gorman here from Codemanship with a longer than usual screencast on the subject of triangulation in test-driven development. Now, if you've been on one of my courses or if you've been reading about test-driven development or practicing it for a while, you may well have come across this term triangulation. Triangulation is the practice of generalizing our designs one failing test case at a time. And it's something that causes a lot of confusion. There's a bit of an art to it. It's quite a mysterious thing that a lot of people don't really get their heads around. So I wanted to make a video to illustrate not only what triangulation is, but hopefully illustrate what it isn't. I think it might be quite useful to see some examples of not doing triangulation to sort of help explain what triangulation actually is. So I'm going to be doing the famous Fibonacci code, sequence generator code kata. It's a slightly different version of the one I normally do. In this simplified version, there are no constraints on the length of the Fibonacci sequences that we can ask for. So this is going to be slightly different to the one that we do on the course, but hopefully it'll work out just the same. So let's start by doing something that definitely isn't triangulation. Let's start by writing a failing test. Let's write a test that's kind of typical of the kind of test that I see people writing when they tackle this problem on the training course that I do. So they write a test something like this and say, well, the first 8 numbers that should be returned should be something like this. Let's ask for a sequence of 8. Remember, in this particular version of the exercise, there are no limits on the length of the sequence. Let's declare our Fibonacci sequence generator class so that we can get our test to run. Let's declare this method for generating the sequence. Let's give that a more meaningful parameter name. Okay, and when I run this test, it should fail because the array is null. So our assertion is failing. I'm happy with that. That's a good reason for it to fail. Now, I could go in here and say, okay, well, I know what the algorithm is that I'm aiming for here. So let's write our Fibonacci sequence generating algorithm to pass this first test. Let's iterate over the array. Now the rules are that for the first 2 numbers, in other words, if the index is less than 2, then we just need to populate that slot in the array with the value of the index. Otherwise, we need to populate that slot with the previous 2 values. So I see people doing this quite often. They write a test that asks, a question like, what are the first 8 numbers? And then they jump in and they write what they think is the simplest solution that will pass that test. And indeed, it does pass the test. So far, so good. Except that, let's imagine we're tackling a slightly more complex problem. What you do see in the real world on real projects is developers will go in, and particularly developers who are used to writing unit tests. Developers will go in, they'll write a test that bites off a big chunk of the requirement. If you think about it, all of the logic of our sequence generator needs to be called into play in order to generate these first 8 numbers with some kind of algorithm. So we have a test that asks, it's not asking one question, it's asking a bunch of questions. What's the first number, what's the second number, what's the third number, and so on. And then we're having to jump in and write a general algorithm to pass that test. So it's not uncommon to see developers who think they're doing test-driven development, they'll write a failing test and then they'll spend half an hour, the morning, or the whole day writing the solution that will pass that test. So for quite a long period of time, their code is not working. Their code is broken. They've got a failing test. And if you're a particular fan of continuous delivery, we want as much as possible for our code to be in some kind of shippable state. That means the code's got to be working as much as possible. So we don't want to be making these big leaps. Write one test and then make a big leap, and then write another test and take a big leap. We want to be taking smaller, safer steps. The analogy I use is you're trying to cross a lake. You're trying to get from one shore to the opposite shore. You're trying to cross the lake using stepping stones. So there are stepping stones in between the two shores. What you don't want to do is you don't want to try and leap from one shore to the opposite shore, because it's quite possible that you will fall in and get wet or drown even. So that's quite a dangerous leap. What you try to do instead is you try to get across the lake by taking smaller, safer steps, so that with each step you're moving forwards towards the opposite shore, towards your destination. But there's less chance that you'll fall in with each step. Each step doesn't require you to take those big leaps. So what we want to do, if we're triangulating this problem, if we're going to solve this problem by generalizing through a sequence of test cases, taking these small steps, let's do it again. Let's delete this Fibonacci class. Actually, let's delete the test that relies on it. And then let's delete the Fibonacci class. Okay. So if we're starting again, this time, rather than biting off a big chunk, sort of leaping in feet first and trying to get to the opposite shore in one bound, we're going to take a small step. So we're going to ask the simplest question we can think of that relates to this Fibonacci sequence. And the simplest question I can think of asking is, what is the first number? The first number in the sequence is 0. So that's our first stepping stone. Let's write a test for it. So Fibonacci generate, and because in this particular version of the exercise there's no limits on the length of the sequence, I can just ask for a sequence of 1 so that I can get the first number. And we're interested not in the sequence, but we're interested in what's in the first slot in the sequence. What's the first number? Let's create our Fibonacci class. Let's declare this method again. Okay. Okay, now this time when I run this test, let's just see it fail. Now this test is failing because of a null pointer exception. That is, the assertion's not failing. We're not even evaluating the assertion. We don't get that far. I want to know what happens when the assertion fails. I want to know that this is a valid test. That is, if it was the wrong number, the test would fail. So let's put the wrong number in that first slot and see what happens. Does the test fail because the assertion fails? Yeah, good. Okay, so if it was the wrong number, the test would fail. So I'm happy with that. Let's do the simplest thing possible to get the test to pass. Okay, we have a passing test. Now what I want to do is I want to look for the next nearest failing test, the next nearest stepping stone that would represent progress towards a general solution. And that would be the second Fibonacci number. Since we've hard-coded the response for the first one and we don't even have a second Fibonacci number, we can be fairly sure that this test will fail. And this time we'll ask for one of length 2, and we'll ask what's in the second slot. Now again, when I run this test, it's going to fail for the wrong reasons. It's going to fail because there is no second element. We get an index out of bounds exception. So again, I'm going to do the simplest thing possible to see this test fail for the right reasons, to see the assertion fail, so that I know that it's a valid test. Now, I can very simply do this to pass both of these tests. So far, so good. We've got 2 passing tests. We've got a solution of sorts, and the solution is very simple. But is this solution more general than the previous one? That's the question I'm asking myself. This is the art of triangulation. We would hope, we would strive with each step forward in terms of failing tests, that our solution becomes more general. And going back to our stepping stones analogy, we want each step that we take to move us closer to the opposite shore, to move us closer to a destination that we're aiming for. And what we're kind of doing here is we're kind of going sideways. I can see what would happen if I then moved on to the third Fibonacci number and then maybe the fourth and the fifth. I could end up typing out the entire Fibonacci sequence forever. And that, of course, is not a more general solution. So I can kind of see where we're going with this. We're not going forwards, we're going sideways. So what I need to do at this point is look for a pattern for those first two Fibonacci numbers. And the pattern looks something like this. Just for these first two numbers. Now that is obviously more complex than what we had before, and we could argue till we're blue in the face about the merits of that or otherwise, but I could kind of see where this was going. I could see myself just hard coding more and more and more and more, and I wanted to take a step forward. I believe this is a step forward because it's more general. We've gone from a sequence to a loop. And there's a great blog post by Robert Martin on the transformation priority premise, which sort of formalizes an idea that quite a few of us were having over the years about these sort of patterns of generalization. I call them triangulation patterns, patterns of generalization. So you might start by hard coding a literal value, and then you might turn that from the next test case into a variable. And then that variable, if you've got more examples, might turn into a list or a collection. And then that collection you might end up turning into a loop because there's a rule that applies to all the elements in that collection, and so on and so forth. So these patterns of generalization that for me feel like you're moving forward, you're moving towards a general solution or a more general solution. So this is the pattern for those first two numbers. So it feels like I've taken a step forward. And when I examine the algorithm that I've got up to this point, even though it's all I need to pass those first two test cases, not a general algorithm for a Fibonacci sequence, it's beginning to take on the shape of that general algorithm as I might recognize it. And this is, I think, where a lot of people struggle. In test-driven development, it's completely false. Some people, some critics of TDD and some proponents as well, have sort of built up this myth that in TDD we don't think about the design up front at all. That is to say, in this particular example, we have no idea what the algorithm looks like for generating a Fibonacci sequence. That simply isn't true. It is very, very useful to have, at the very least, a very vague picture of what you think the end solution might look like, so that you can recognize it when you see it, and so that you can tell whether you're getting warmer, whether you're getting closer to it. So this is beginning to look more like some kind of iterative algorithm, which I would expect the algorithm to be. So it feels like I'm getting warmer, I'm moving in the right direction. So with that nice warm feeling, let's do a little bit of cleanup here and get rid of a little bit of duplicate code here. Get number at index. And let's parameterize this. Now there's a relationship between these numbers. If I parameterize the index, there happens to be a relationship between the length of sequence I ask for and the index, such that I ask for a length of index plus 1. So far so good. So I can now reuse that here. Now remember, in this version of the exercise, the length is not constrained in any way. Here we're asking for an index of 1. Let me just move these out of the way, so that all our tests are together, and the helper code is further down. Okay, now we can move on to our third test. Now if I wasn't working in JUnit, I'd be parameterizing these tests at this point, but I find parameterized tests in JUnit such a pain in the arse that I'm not going to bother. Right, the third Fibonacci number is also 1. So I'm interested in this test because the implementation we have at the moment will put the index in the slot, and the index is 2, so that's the wrong value. So we're expecting the value to be 1 and an index of 2. And we believe this test will fail because it's going to put the value 2 in that slot, which indeed it does. Okay. Now here we need to branch because the rule that we've got so far will always apply to those first two numbers. So let's tie that off and say, okay, for those first two numbers, in other words, if the index is less than 2, then do what we were doing before. That will always be true. Otherwise, we want to do something else. Now, here's again where I see a lot of people on the training course coming unstuck. The temptation is to say, well, the rule is that. And we know this because the algorithm has been dangled in front of us. It's very simple. It's very tempting to say, we can do that and that will pass the test. And indeed, if I run it, it will pass the test. Oh, that's interesting. Oh, yeah, of course. This is why we write tests. Another nice side benefit of doing test-driven development. Okay. Now, although that passes the test, it is in fact not the simplest thing I could have done. To pass those 3 tests, all I really needed to do was that. So I could have done it taking a smaller step. And generally speaking, it's a good idea, unless it's something totally trivial that couldn't possibly go wrong. Generally speaking, it's a good idea to take the smallest steps you can find in terms of implementation. So that's the smallest step I can think of that will pass that 3rd test. So now let's move on. What is the next nearest failing test, the next nearest safe stepping stone that would be progress towards the opposite shore? Well, the 4th Fibonacci number, it's got an index of 3, but we're going to be putting a hard-coded 1 in that slot when the value should be 2. The 4th number is 2. At index 3. So this will fail because it's actually going to put a hard-coded 1 in that slot, which indeed it does. Again, now we're faced with this temptation of saying, oh, well, at this point, we can do this. And that will indeed pass the test. But again, it's not the simplest thing we could have done. We could literally just do that. So when the index is 3, the value is 2. When the index is 2, the value is 1. That does pass the test, and it's another step forward. It's another generalization. Okay, now what about the 5th Fibonacci number? Well, it has an index of 4 and a value of 3. So our code, as it currently is, will actually pass that test, or we would expect that it would. So this is not the next nearest failing test. It doesn't represent progress in terms of solving the problem. So we're going to skip the 5th Fibonacci number and move on to the 6th Fibonacci number, which has an index of 5 and a value of 5. 6 numbers, right? Is 5. So I believe that it's going to put 4 in that slot with the current implementation, and indeed it does. Now, at this point, going back to our analogy of stepping stones, at this point we're standing on a stepping stone that is right next to our destination, is right next to the opposite shore, such that we could just step off it. The opposite shore is just another stepping stone. And the simplest generalization we can make at this point just happens to be the general pattern for all Fibonacci numbers with an index greater than 1. Okay, so we have triangulated the problem. Rather than doing it in one big leap, just writing one test and writing a general solution, we've worked through a sequence of failing test cases, always looking for the next nearest failing test, the next nearest safe stepping stone, and then generalizing the solution as we go. The art to it is in walking that very fine line between overgeneralizing too early and not generalizing enough. So in the first example, when I just wrote one test and then we wrote the implementation, you could argue that I wasn't necessarily overgeneralizing because we had a whole bunch of Fibonacci numbers that we had to calculate. But I could have just hard-coded those 8 numbers and that would have been simpler. So I did generalize too early. And again, we've seen several points within this particular exercise where I could have generalized too much too early. Conversely, it's possible to not generalize enough. So for example, we could have carried on hard coding Fibonacci numbers into the array, and that would have passed the tests, but it wouldn't have been the correct solution. It wouldn't have been a general solution. So we've been walking that tight line, and one of the benefits of doing that, apart from the fact that if we take these small steps, our code is working more often and for longer, one of the other benefits is we end up with a test suite that sort of, I like to use the expression, it hugs the code. Our tests hug the code. Because we've written more tests and taken these smaller steps, there are less gaps between the questions the tests are asking and the implementation that we have to answer those questions. And because we're leaving less gaps in our test coverage, what that means is when our implementation breaks for whatever reason, it's more likely that one of these tests will fail. So our tests hug the code. So that's another benefit of triangulating. So that's triangulation. People then will often ask on the training course, well, how do we know when we're done? You know, how do we know when we're finished? And the answer to that is very, very simple. The point at which you're done is the point at which you can't think of any more failing test cases. You can't think of any more tests that should fail with the implementation you've got. And that's where we are now. As theoretically, for any value of the index and for any length of sequence, we should get the correct Fibonacci number or the correct Fibonacci sequence. Having said that, let's do a little experiment. Let's imagine that we want to test at some larger value here. We just want to make sure, we just want to double check. So let's ask what the 50th number is. Now, I haven't actually looked it up, and it is indeed a very big number that takes a long time to type out. So I'm just going to say that the 50th number is huge, and I'm going to write a test that says that our 50th number, which has an index of 49, should be a value greater than, certainly greater than a billion, like that. Now I don't know what the number is, but it's certainly greater than a billion. So if I was writing this test for real, by the way, I would look the number up. But since we're pushed for time, so when I run this test, theoretically it should pass because it will calculate a number that we know is greater than a billion because it's a huge number. And it's calculated correctly. So let's just run that test. And it fails. It fails, and I'm not really sure why it's failing. It's not giving us many hints there. It's just our assertion is failing. Now, I've done this before, and I happen to know why this is failing, and I'll just demonstrate why it's failing. It's because the 50th Fibonacci number is so long, so big, so huge, that in actual fact, it won't fit inside a Java int. If we make it a log, suddenly it works again. So why am I demonstrating that? Well, I want to make a point here, which is that the whole point of TDD and of triangulating is not to test our software. And nobody has ever said that if you're doing test-driven development and if you are triangulating, that you won't need to write more tests. No one's ever said that. In fact, I think it's a very good idea, particularly if it's code that you're not entirely sure about or it's something that's critical to your application. You may wish, using your judgment, to go further and write more tests. But if we're expecting that the code should pass those tests first time, then that's not TDD. That's just what we call testing. At that point, we're looking for bugs in the code. TDD is not about looking for bugs in the code. The tests that triangulation leaves behind hopefully are good enough that it is unlikely that the code will be broken without some tests failing, but it is not impossible, as we've just seen. So that's triangulation. It is the art of generalizing our design one failing test case at a time, taking small steps. So using that analogy of stepping stones, we're looking to take small, safe steps that mean that we won't have to take big leaps that risk us falling into the deep water. So that's triangulation. I hope that's been of some use, and Happy New Year.